There are several functional approximations of the Bark scale that can be used for this mapping, and an overview of them can be found here on this website. So we have different Bark scale approximation that includes the Zwickler and Terhard, the Wang, Seke, and Cashew. We have the Schroder, the Traunmüller, and there's some basic explanation here on this overview of Bark scale approximation. The approximation that we previously saw is from the analytical expressions for critical band rate and critical bandwidth as a function of frequency, which is an article in the Journal of the Acoustical Society of America by Zwickler and Terhard, and you can take a look here. And in Python notation, the approximation is given here with f in Hertz and z in Bark. And we can see that it has an approximate closed form inverse formula according to this reference here. And we have this equation here. So we can test this Zwickler and Terhard approximation using Python. And this is what we are doing here. Here we will have a frequency array between 0 and 20 Hertz in 1000 steps. So this is what we are in here. Here we are having the computation of the Zwickler's Bark approximation formula that we've seen before, and we're just plotting. We can also test the inverse approximation, and we do the same thing. We have the frequency array between 0 and 20 kilohertz in 1000 steps. We make the computation of this Zwickler Bark approximation formula and the computation of the inverse. And here we can plot the reconstructed frequency over the original frequency. And that's what we see here. Here we have the identity, and here we have the Zwickler forward and inverse. Another important approximation is the Traunmüller approximation that comes from the 90s, and it was presented at the Analytical Expressions for the Tonotopic Sensory Scale at the Journal of the Acoustical Society of America. And in this approximation we have a simple notation in Python for above 200 Hertz given here and below 200 Hertz given here, and it has an exact inverse also for above 200 Hertz and for below 200 Hertz. The last approximation we are going to talk about is the Schroder approximation that is from the late 70s, and it was presented at the Recognition of Complex Acoustic Signals from Signal and Life Science Research report. And you can also see something about this at the Perceptual Linear Predictive Analysis of Speech from the 90s. And it's also used in the PEAK standard for objective quality estimation. And here we have this paper for PEAK, the ITU standard for objective measurement of perceived audio quality. And if you read about, you'll find about the Schroder approximation. It has a simple approximation given here, and it also has an exact inverse from Bark to Hertz given here. So now we are going to compare all these approximations. So the comparison of our functional approximations with our Bark table, and we see that the approximation formulas, they also give fractional Bark numbers, and the integer Bark numbers correspond to unique frequencies, which are band limit. Tables name bands after an integer Bark number, but they differ in if the band above or below is named after that number. So in the lecture table, we've seen this integer Bark number corresponds to the lower limit of the band, hence it starts with index 0. And we find in other literature, for example, if you look at the Karma materials and in Wikipedia, it corresponds to the upper limit starting with index 1. So we need to be aware of these differences in literature. We will use the pairs out of the table for comparison. So 1 bar will correspond to 100 Hz, 10 bar to 1070 Hz, 15 bar to 2700 Hz, and then also these values for 20 and 22 bar and the corresponding values to Hertz. And now what we'll do is that we will plot all these approximations. That's what we are doing here. So we have the Traumüller, the Schroder, the Zwicker, and here is our comparison. So we have the approximations of the Bark scale. Here we have the frequency in Hertz, and here we have the corresponding Bark domain. So observe that the Zwicker approximation is the most precise and it hits our test points, but the problem is it has no closed form inverse. The Schroder approximation is the least accurate, but it is the simplest and it has an exact inverse in closed form, hence it's used most often, and we will also use the Schroder approximation. And just as we mentioned before, we use the Hertz to Bark, and here we see that this is the Schroder approximation. If we go back here and we look at the Schroder, here's the Schroder approximation. So in Bark is 6 times the arc sine h of the frequency in Hertz divided by 600, and our function Hertz to Bark is 6 times the arc sine h of the frequency in Hertz divided by 600. And this is the Hertz to Bark that we've been using. And also the Bark to Hertz, it uses the exact inverse. It's given by 600 times the sine h of the Bark divided by 6. And this is what we see here. So this function we've been using before, it's using this approximation given by Schroder, which is not a perfect approximation, but as we've seen before, it is the simplest approximation, and it has a closed form inverse, which makes life much easier for us.